Welcome to AI Paper Slop. Today we are unpacking Sana Video 2.0, Hybrid Linear Attention with Attention Residuals for Efficient Video Generation, a new paper from NVIDIA. And the core insight we're starting with today is that video diffusion transformers, or DITs, are currently just crippled by the order n squared cost of full 3D softmax attention when you're handling tens of thousands of tokens.
Right, it's a complete computational nightmare.
Exactly. So Sana Video 2.0 basically solves this with a hybrid architecture. It's 75% gated linear attention for that order n efficiency, and then 25% gated softmax anchors, which restores the full rank token interactions. And to stop the linear layers from becoming a bottleneck, they use something called Block Attention Residuals, or AttnRes, which routes completed softmax enriched summaries directly into later linear layers.
Which is such a clever routing trick.
It really is. And the result is just staggering. Their 5 billion parameter model hits a vBench score of 84.30, matching those massive full softmax models, but it generates a 720p 5-second video in just 13.06 seconds on a single H100. That is like 120 times faster than one 2.2 A14B.
Yeah, and what's genuinely fascinating here is that they didn't just, take a massive pre-trained softmax model and do some post-hoc linearization to make it run faster.
Which is pretty much the standard shortcut, right?
Oh, absolutely. The whole industry is doing that, train heavy, prune light.
Yeah.
But here, NVIDIA built a unified 5 billion and 14 billion architecture and trained it entirely from scratch. And to pull that off without the model just, collapsing, they had to utilize a highly specific data curriculum and a really clever, content-aware, time-step sampling method.
So to understand why a team of researchers would just throw out the standard playbook and build this hybrid from scratch, we first need to look at, the physical limitations of the hardware we're all using. We need to understand why pure softmax on one hand and pure linear on the other both basically hit a brick wall when you try to scale video.
Right. Let's look at the sheer volume of data first. I mean, even when you use a highly efficient VAE and autoencoder to compress your raw video into latents, and they used LTX VAE 2.3 here, which is incredibly aggressive on compression.
It's super compressed, yeah.
Even then, a single 1080p clip still spans tens of thousands of latent tokens. And with standard full softmax DITs, every single one of those tokens has to calculate its relationship to every other token.
Which creates that massive quadratic attention matrix.
Exactly. The sequence length is just so huge that the order n squared complexity completely shatters your activation workspace on the GPU.
Right, which makes linear attention look like the obvious, magical fix. Because it operates at ordered n complexity, meaning it scales linearly with sequence length. If you double the video length, you literally only double the compute.
It sounds perfect on paper.
Right. So the immediate question any ML engineer listening would ask is, why not just use 100% linear attention and just never worry about memory bottlenecks again?
Well, because you run headfirst into the low-rank dilemma. Pure linear attention has this fundamental mathematical limitation in its capacity. It essentially compresses all the token interactions into a fixed-size state matrix, let's just call it S, with dimensions d by d. That creates a hard physical bottleneck on the rank of the matrix. The linear attention mechanism simply does not possess the mathematical dimensionality to represent every single token-to-token interaction.
Okay, let's try to ground that in reality for a second. So pure linear attention is kind of like trying to have 10,000 people in a massive stadium, and they're all trying to talk to each other, but you only give them, say, 10 walkie-talkie channels.
That is exactly it.
The system just physically doesn't have the bandwidth for every individual conversation. So the fine details get completely drowned out in static, and you only get the loudest, most generalized noise.
That's a perfect way to visualize that rank bottleneck. And when you're generating high-fidelity video, you absolutely require precise, high bandwidth spatio-temporal correspondence. I mean, you need the model to know exactly how a shadow moves across a cheekbone over the course of 30 frames.
Right, micro details.
Yeah, and pure linear attention just smears all that detail out. It physically lacks the channel capacity to hold those specific granular relationships.
But wait, hold on, let's unpack this. If linear attention is fundamentally bottlenecked like those 10 walkie-talkie channels, how does combining the two actually solve anything?
What do you mean?
Well, if you mix a high bandwidth connection with a low bandwidth connection in a sequential network, doesn't the low bandwidth part just, choke the whole pipeline anyway and degrade your output?
You would definitely think so, and that exact tension is what this paper brilliantly navigates. It leads us straight into the core architectural design of Sana Video 2.0, which is how they interleave the two types of attention. The layout they settled on is a 3-to-1 ratio.
Okay, so 3 linear to 1 softmax.
Exactly. You have 3 gated bidirectional linear attention layers, followed by 1 gated softmax anchor layer. So the whole architecture is 75% linear and 25% softmax.
And the science behind picking that specific 25% ratio is actually what I loved most in this section. They didn't just guess or pick a nice round number for the sake of it.
No, they were very methodical.
Yeah, they ran exhaustive proxy studies using smaller models, specifically depth 28, with 3072 models running at a 256p resolution. And they tested the entire spectrum, from 0% softmax, purely linear, all the way up to 100% full softmax.
And the loss curves on those proxy studies map out this fascinating trade-off space. The 50% hybrid, so interleaving 1 linear layer for every 1 softmax layer, actually achieved the lowest overall loss out of everything at 0.897.
But they didn't deploy the 50% ratio.
No, because they were optimizing for a real-world inference budget.
Yeah.
That 50% hybrid came with a pretty steep 1.29x latency penalty over the 25% hybrid. The 25% hybrid, that 3-to-1 ratio they ultimately went with, had a loss of 0.905.
Which is incredibly close to the 50% model's performance.
It is, but it runs significantly faster. They identified that 25% mark as the optimal quality to efficiency Pareto knee. It's the exact inflection point where you get the most expressiveness for the absolute least amount of compute.
Right. And there is another massive hardware-friendly change in this section that I definitely want to highlight. In their previous iteration, Sana Video 1, they used a temporal convolution feed-forward network, an FFN. But for version 2.0, they ripped it out entirely and replaced it with a convolution-free SWIGLU FFN.
Yeah, and if we zoom out to the broader challenges of hardware acceleration, that temporal convolution was basically a ticking time bomb for scalability. The paper details how the latency overhead from the temporal convolution just spiked non-linearly as video duration scaled up.
It was bad.
It grew from adding just 12 milliseconds of latency for short clips to a massive 117 milliseconds at 60-second durations.
So why does a temporal convolution break down so badly at scale compared to like a SWIGLU?
It comes down to how standard off-the-shelf attention kernels like flash attention are actually designed under the hood. They assume pointwise FFNs. They optimize memory access in these blockwise chunks that fit perfectly into the SRAM on the GPU.
The super fast on-chip memory.
Right. So when you introduce a temporal dimension like a 3D convolution, you completely break that localized memory access pattern. The GPU suddenly has to pull data across time, which means going all the way back to the slower HBM, the main memory. SWIGLU, on the other hand, is completely pointwise. It plays incredibly nicely with modern compiler optimizations because it keeps all the memory access localized.
Okay, so they've engineered this brilliant, highly optimized 7525 architecture that the compilers just love. But circling back to my earlier pushback, we now have these periodic smart softmax layers that restore all those high-resolution stadium-wide token interactions.
Right.
How do we ensure the dumb linear layers actually benefit from them? Because in a standard sequential network, those linear layers would just be operating on their own constrained low-rank state matrix again, right?
And this is where the major architectural breakthrough of the whole paper comes in. Block Attention Residuals, or AttnRes. In a standard transformer, you rely on additive residuals. Layer 2 just adds its output to Layer 1, Layer 3 adds to Layer 2, and so on. But additive residuals kind of force later layers to essentially rederive or just blindly pass along the complex spatial information that was already computed upstream.
It's like playing a really terrible game of telephone. The signal just degrades as it gets passed down the line.
Exactly. So to fix the telephone game, AttnRes actively routes completed block summaries directly across the depth of the network. They grouped every 8 layers into a computational block. And the router at any given layer doesn't just look at its immediate predecessor.
What does it look at?
It pulls from a highly specific source set. The initial patch embedding, the completed feature summaries from all the previous 8-layer blocks, and the current in-progress partial sum of its own block.
Okay, here is where my skepticism really kicked in while reading the paper. They say they share a single routing query across all depths to save memory. That makes no sense to me intuitively. If you use the exact same query vector at layer 2 and layer 30, aren't you just forcing the network to pull the exact same information at every single stage?
It seems like it would.
Doesn't a static query completely destroy the adaptivity you want from a routing mechanism?
It's a really counterintuitive design choice, I'll give you that. But the routing actually remains incredibly selective. The mechanism that makes it work is normalization.
Oh, interesting.
Yeah. The source features themselves are normalized per token using RMS norm, and that happens before the shared query is ever applied. So even though the query vector itself is static across all the depths, it is constantly interacting with a dynamically changing token-specific feature space. That localized interaction is what produces highly adaptive dynamic routing weights for every single token, at every single layer.
Oh, wow, that makes total sense. The query doesn't need to change if the landscape it's querying is perfectly normalized and context-aware. So the network is still making smart, layer-specific choices about what data to fetch.
It is. In fact, the routing distribution physically proves it. The router heavily favors recency, which aligns perfectly with how sequential models refine representations. The paper breaks down the routing mass, and it shows that deep layers, specifically layers 25 through 32, pull a massive 56% of their attention routing mass directly from those completed block summaries.
Wow.
And out of that pool, the most recently completed block gets about 26% of the weight.
Which proves structured representation reuse is actually happening. The linear layers are actively fetching the high-fidelity updates computed by the previous softmax anchors rather than trying to, calculate them from scratch.
The measurable result of toggling this AttnRes feature on is just fantastic. They actually quantified the effective rank of the states in the deep linear layers. With AttnRes engaged, the effective rank increases by roughly 12%.
So it is physically recovering that missing mathematical expressiveness. To go back to our metaphor, the 10 walkie-talkie channels are basically figuring out how to multiplex and carry significantly more data because they're borrowing the high-resolution map from the softmax layers.
Exactly. It's a beautiful synergy between the network topology and the attention mechanics. But, as anyone listening who actually works in ML knows, the most elegant novel architecture is entirely useless without the right training recipe.
Oh, 100%.
If you just feed this model standard, noisy web video, all that architectural elegance just goes straight to waste. The way Sana Video 2.0 is trained from scratch is arguably just as critical as the hybrid attention mechanism itself.
So let's unpack the data dilemma, because this is something every video generation researcher is battling right now. High quality, perfectly sharp, aesthetically pleasing video clips are usually totally static. Think of a slow, stabilized drone shot over a mountain range.
Right.
On the flip side, clips with complex, dynamic, high-motion scenes, like a person doing a backflip or a dog catching a frisbee, almost always suffer from visual artifacts, motion blur, or compression noise.
So if you set a single rigid training threshold for quality during your data filtering, you force yourself into a lose-lose scenario.
Yeah.
You either train a model that generates gorgeous still images that barely move, or you train a model that generates highly dynamic but incredibly ugly artifact-ridden video.
You want the model to learn physics from the high-motion clips, and you want it to learn aesthetics from the low-motion clips, but you don't want it to confuse the two. How do you feed it both without polluting the weights?
Their solution is an innovation called TQD, or the Time-Step Quality Motion Funnel. It operates as this really elegant content-aware flow shift mechanism. In diffusion and flow matching models, different noise levels physically teach the network different things.
Right.
High noise states, where the image is mostly just structural static, they govern the global composition and large-scale motion. They completely mask fine textures anyway, so compression artifacts in the training data don't actually matter at that stage. Conversely, low noise states, near the clean image, are where the model learns fine visual detail.
So NVIDIA engineered the training pipeline to route the data based on its physical properties.
Exactly. They alter the probability distribution of the time-step sampling using a logit shift. High-motion clips, which we know might have lower aesthetic quality, are physically pushed toward the high-noise regimes with a plus 1.1 logit offset.
Yeah.
Aesthetically clean, low-motion clips are pushed toward the low-noise regimes with a Nagios 1.1 logit offset.
For the ML engineers listening, think about the math of that offset. A logit shift physically skews the probability distribution of which time step is sampled during a training batch. You are literally forcing the model to spend more training steps looking at the high motion data when it is focused on global physics, and forcing it to look at the static, beautiful data when it is focused on fine textures.
And evaluating this TQD training process led to what I consider the biggest cautionary tale of the entire paper.
Oh, the validation metrics?
Yes. Typically during training, you monitor your progress by tracking the standard random time mean validation loss. You just average the loss across all the random time steps to see a single scalar number that tells you if your model is improving. NVIDIA's team realized that for video diffusion, doing this makes you completely blind.
It's worse than blind, it's actively misleading. Because the loss varies so drastically across the noise axis, a single scalar mean just blurs the actual signal completely.
So instead of tracking a single mean, they stratified their validation into 10 distinct noise buckets. And the data they gathered from tracking 4 paired checkpoints is just eye-opening. If you just looked at the overall mean loss, it improved by 6.4%. Most engineers would look at that and think, great, ship it, the whole model is getting better.
But when you look at the 10 stratified buckets, the story completely flips. The low noise buckets actually improved by a massive 11.4%, which dragged the overall mean up. But the highest noise bucket, the one responsible for global structure and motion, actually regressed by 1.2%.
If you were only tracking the mean, you would have deployed a model that was actively getting worse at generating physics in coherent motion simply because it was getting marginally better at rendering textures.
It's crazy.
By stratifying the validation, they gained this precise surgical monitor of the model's true capabilities across the entire generation spectrum.
It is such a practical, vital engineering detail that immediately changes how you structure your validation loops.
Okay, so all of this, the 75-25 hybrid architecture, the block attention residuals increasing the effective rank, the TQD data funnel shifting the noise schedules, it all culminates in the final inference speed and hardware scaling metrics.
Okay.
And the numbers they achieved are just staggering. Let's walk through those benchmarks. The Santa Video 2.05 billion parameter model achieves a V-bench score of 84.30. That places it squarely in the top tier of competitive generation quality. It's not sacrificing visual fidelity. But the raw throughput is where it really shines. Its compiled DIT forward pass is 3.2 times faster than a matched full-softmax baseline at a resolution of 720p and 60 seconds of video.
And the NVIDIA team didn't just stop at the raw architectural speedup. They took this model and wrapped it in a full-stack optimization pipeline they call the Soul Engine.
The Soul Engine pushes the hardware to its absolute limits. It leverages custom kernel fusion, aggressive caching strategies, and most importantly, sparse attention specifically targeted at those 25% softmax anchors we talked about earlier.
What?
When you run this fully optimized stack on an NVIDIA B200 GPU, it adds a further 3.58x speedup on top of the architectural gains.
Wow.
That brings a 5 billion parameter, 720p, 5-cycle video generation pipeline down to an astonishing 13.06 seconds.
13.06 seconds. Just for comparison, the paper points out that this makes it roughly 120 times faster than running one 2.2 A14B on a single H100. That is not an incremental improvement. That is a generational leap in usability. You are taking workloads that used to run overnight and bringing them closer to near interactive speeds.
Furthermore, they prove that this architecture scales seamlessly across parameters and hardware generations. They also trained a massive 14 billion parameter version, expanding it to 40 layers and a width of 4096. When they profiled this larger model, it ran 1.69 to 2.02 times faster on the new GB200 architecture compared to the H100.
So it's future-proof.
It proves that this hybrid, order-n-dominated backbone isn't just a bespoke quark optimized for one specific chip. It maps cleanly onto the block-level architecture of newer hardware and scales up beautifully.
So we've unpacked the physical limitations of quadratic attention, the 3-to-1 ratio, the residual routing mechanism, and the stratified training strategy. For the researchers and developers listening, how does this actually change the landscape? Like, where does this lead us?
One of the most provocative, easily overlooked details in this paper is a slight mathematical choice they made in the linear operator. The gated linear attention operator in Santa Video 2.0 intentionally drops the causal delta rule update.
Okay, meaning what?
It's designed strictly as a bidirectional gated bilinear form because standard video generation looks at the whole sequence at once, past and future frames. But because they dropped that update, the authors point out that this specific scratch-trained backbone serves as a mathematically perfect initialization for a causal gated delta net.
Oh, wow. So you could take this exact architecture, which we just established, can perfectly simulate physics, motion, and lighting in an offline video generator with a 120x speedup, and you could just flip it to be causal.
You could adapt this highly efficient, rigorously trained, kernel-friendly recipe directly into autoregressive causal generation.
Think about the implications of that for a second. Imagine taking this exact recipe and applying it to closed-loop streaming world models. We're talking robotics, autonomous driving, real-time embodied AI. If a 75% linear attention backbone is expressive enough to perfectly simulate the physics of a splashing teacup or a running cheetah in a generated video, what happens when you put that hyper-efficient order-n scaling architecture into a robot's brain?
It fundamentally shifts what we consider computationally viable for real-time spatial intelligence. The ceiling for how much context a system can hold before latency breaks the loop just got significantly higher. You could process massive, continuous spatial temporal context windows in real time, on the edge, without a quadratic memory bottleneck immediately melting your hardware.
And it all started by figuring out how to give those 10,000 people in the stadium the exact walkie-talkie bandwidth they needed, precisely when they needed it. It is something to keep in mind the next time you're blindly relying on a standard softmax transformer. Keep experimenting, keep questioning your validation metrics, and we will catch you on the next deep dive into the slop.